All right, what do you want to see first? All of it.
79.
All right, let's take a look at number 79. The directions for this one tell us to evaluate the definite integral, and then we can check it on a calculator if we want to. So on 79, we've got the integral of that quantity x minus 1 times the square root of 2 minus x dx. So we have two quantities in this one, and you might guess either one of them, really, okay? But I'm going to go with the one that has an exponent of something besides 1. That's more likely. So I'm going to let u equal that quantity right there under the square root sign. So I'll let u equal 2 minus x. And if that's what u equals, then I compute du. So du equals whatever the derivative of 2 minus x is, which is negative 1, times dx. So that gets me there, that gets me there. Then I look back up at my problem, and I see that, I can rewrite that as the square root of u, so I'm in good shape there. And then there's not a negative dx. So I'd rather have dx. So right there on that line, I multiply both sides by negative 1. That means the two things I have boxed up then, I can replace with u, with expressions of u or du, okay? But I've still got that x minus 1 hanging out in front. Well, I can't do that. Well, I can, but it'd be wrong, all right? If I make that the square root of u and I make the dx into a negative du, I can't work that problem. I've got u's and x's. So not good enough. Either I've got to try a different u, or I've got to see if I can come up with some way with what I have to make this work. And that's what I need to do. So when I go back to this line right here, u equals 2 minus x, I need to solve that for x. So I can subtract 2 from both sides, make that u minus 2 equals negative x, and then multiply everything by a negative 1, so I get a positive x, I get a positive 2, and a negative u. So x equals 2 minus u. So now, I'm still not ready to mess with those limits of integration yet. Will this substitution work? Let's see if it will. So I've got the integral. The square root of 2 minus x is now the square root of u. Dx can be replaced with negative du. So then what can I do with this x minus 1? Well, I can replace the x with what it equals, 2 minus u. 2 minus u. And then minus 1, all right, 1's good, minus 1. I've got everything in terms of u, and it looks like if I simplify a bit and then distribute that square root of u, I'll be able to turn that into something I can take the antiderivative of. So I'm satisfied with that. But I've got to change my limits of integration, because those limits of integration are x coordinates. I don't have x in my problem anymore. I have u, so I've got to change them to u. And here's how I do that. If x equals 2, so I'm looking at the upper limit of integration. If x equals 2, then what does u equal? Well, if x equals 2, u equals 2 minus 2, so u equals 0. So the upper limit of integration as u is 0. Then I look at the lower limit of integration. If x equals 1, then what does u equal? Well, if x equals 1, u equals 2 minus 1, so u also equals 1. So my upper limit of integration is now 0. My lower limit of integration is now 1. When I put all of that together, I get this. So, you with me down to the yellow? Because if we can make it to the yellow, I think we'll be able to get this problem. Okay? All right. So first thing I'm going to do is I'm going to simplify inside the parentheses. 2 minus 1 is 1. So I'm going to change that to parentheses 1 minus u. Notice I also went ahead and changed that square root of u to u to the 1/2. I either need to change it or at least in my head change it, right? Now distribute the u to the 1/2. So I've got, oh, look what else I decided to do. I've got the integral from 1 to 0 with a negative sign in front of it, which I can work. There's nothing wrong with that. But one of my properties is I can, if I have the integral from a to b, it's the same thing as the opposite of the integral from b to a. So I'm going to change that, make it the opposite, and the opposite of a negative is a positive, and then switch the limits of integration. I don't have to do that, but I wanted to. So I did that, then distribute the u to the 1/2. So I'm here on this line, and now I'm ready to use the fundamental theorem of calculus. Take the antiderivative, so that'd be 2/3 u to the 3/2 minus 2/5 u to the 5/2, and evaluate it from b to a, from a to b, okay? Which means the antiderivative evaluated for b, the upper limit of integration, minus the antiderivative evaluated for a, the lower limit of integration. I like that 0. Okay, evaluating for 0 in this particular instance was pretty easy. Then all I got to do is crunch the numbers. Yes? I took the antiderivative. Right? Power rule, add 1 to the exponent, divide the coefficient by the new exponent. All right, does that take care of 79? What do you want to see next? 72? Kristen, which one do you want? Which one? 88. All right, 72 and then 88. 72. All right, same directions. Find the definite integral. All right, we've got a quantity with an exponent on it, so I'm going to let u equal that quantity, x cubed plus 8. Once I've decided to let u equal x cubed plus 8, I have to compute du. Well, the derivative of x cubed is 3x squared. The derivative of 8 is 0. So I get 3, so du equals 3x squared dx. So I'm right there. But then this is going to become u squared, isn't it? But I still need to replace x squared dx. X squared dx, not 3x squared dx. So how do x squared dx into an x squared dx? Multiply both sides by 1/3. So 1/3 du equals x squared dx. And I can make the substitution now, can't I? All right, everybody see that I'm going to be able to do the substitution? All right. Now, let's change our limits of integration. So if x equals 4, what does u equal? Well, if x equals 4, u equals 4 cubed plus 8. What is 4 cubed? And then 64 plus 8, 72. So that upper limit of integration is 72. If x equals -2, what does u equal? Well, what do you get when you cube -2? -8. So u equals 0. Like the looks of that. So then we make our substitution. So here's what I was doing. My limits of integration are now going to be 0 and 72. This quantity squared is now u squared. X squared dx is replaced with 1/3 du. So that's how I got that. Everybody with me? All right, I'm in pretty good shape now, aren't I? Because that's an easy antiderivative. The antiderivative of u squared is 1/3 u cubed. So don't forget that you've got the 1/3 out in front. So keep that there. And then the antiderivative of u squared gives us another 1/3 u cubed. evaluated from 0 to 72? Well, as we know, we can factor constants out. So really, if I had just done a little bit better job placing brackets, I could have skipped that step, couldn't I? Because that 1/3 can be factored out. So 1/3 times 1/3 is 1/9. Then we evaluate for 72, get whatever 72 cubed is, evaluate for 0, that's going to be 0. As everybody knows, 72 cubed is 373,248. That's when you had memorized, right?
Yeah.
Okay. And then, as everybody knows, that divided by 9 is 41,472. $72 makes sense? What was it, 88? 88. Yeah. Right on 88. Let's see. It says find the area of the region, and then we can graph it to check. So if you look at the graph in the book, all right, you see that your region goes from -2 to 6. So I made the integral from -2 to 6. The graph is never below the x-axis, so I don't have to worry about trying to break it up and getting a negative signed area and a positive signed area and all that. So I can just go from -2 to 6. And our function is x squared times the cube root of x plus 2. So the integral from a to b of f of x dx will give me that area, since the graph's always above the x-axis, or at least it's never below it. So the integral from -2 to 6 of f of x, which is x squared times the cube root of x plus 2, dx. As we've done, let's let u equal the quantity that has the exponent on it. So let u equal x plus 2. Now compute du. Well, du equals, well, the derivative of x plus 2 is 1. So du equals 1 dx, or just dx. So that means that I'm able to rewrite that as the cube root of u. That means I'm able to rewrite that as du. But unlike what happens so often, I didn't get something to get rid of that along with the du and the dx, did I? Okay? So that means either I've chosen poorly in regards to guessing what u is, or, well, I can go back to u and I can solve that for x. So if u equals x plus 2, subtract 2 from both sides, and u minus 2 equals x. Now, I'm not real thrilled with that, because now I'm going to have a different quantity with an exponent on it. But really, that's pretty much all I can do, because I didn't choose poorly when I chose u. That's pretty much the only u I can try. Okay? So that means when I rewrite this integral, I'll do it over here. That means the x squared is going to have to be u minus 2 squared. The cube root of x plus 2 is going to be the cube root of u. And then dx is going to be du. That's what I got. And I can work that. Can you see at that point that you're going to be able to make that work? It's going to take some algebra first. I'm going to have to square the quantity, then distribute a u to the 1/3. But I can make that work. Now, change the limits of integration. If x equals 6, then u would be 6 plus 2, so u equals 8. If x equals -2, then u equals -2 plus 2, u equals 0. So the limits of integration are now 0 and 8. That gets me there. So the area of that region is going to be the integral from 0 to 8 of u minus 2 quantity squared times the cube root of u du. And now we rewrite the integrand. So you square the u minus 2, and it's not u squared minus 4, not even u squared plus 4. It's u squared minus 4u plus 4 times u to the 1/3 du. So distribute the u to the 1/3. When you multiply factors with the same base, you add the exponents. So 2, which is 6/3, plus 1/3 is 7/3. So that's what I get there. And then 3/3 plus 1/3 is 4/3. That's what I get there. And I'm ready to take the antiderivative now. So use the power rule for integration on each one of these terms. So you add 1 to the exponent, then you divide the coefficient by it. Same thing here, add 1 to the exponent, divide the coefficient by it. Add 1 to the exponent, divide the coefficient by it. Just remember that when you're dividing by a fraction, it's almost always better to just multiply by the reciprocal of that fraction. Then do a little simplifying to get to this step. So take a second to see if you're able to get that far. Well, we do need to be to the point where that's not in much, it's not daunting. It shouldn't be something you look at this point and go, oh, crud, I'll never be able to do that. You better be. Okay. So now we evaluate. We evaluate for 8 first. So we substitute in 8 for u there, there, and there. Then we evaluate for 0. And much to our good fortune, when I put in zeros there, there, and there, I get a 0. Okay, so I'm kind of pumped about that. And then I've got the calculator with me, so I can compute 8 to the 10/3 fairly easily. And even if you don't, well, you'd want a calculator, but 8 to the 10/3 means take the cube root of 8, 2, and raise that to the 10. And I'm still going to want a calculator to do that, more than likely. But I mean, it's not something that's impossible to do. And then the 8 to the 7/3 means the cube root of 8 to the 7th, 8 to the 4/3, cube root of 8 to the 4th. So keep simplifying, and again, use your calculator. Go ahead, have a good time, and there you go. $88 makes sense now? Any questions on 88? All right, 81. On 81, we're just finding the definite integral. We have the integral from 0 to pi over 2 of the cosine of 2x over 3 dx. Now, sometimes we let the theta part of our trig function be the u, and sometimes we don't. And sometimes, if you look at number 82, you don't even need a u. But as a guideline, if you just have the one trig function, then you're probably going to let the theta part be the u. It's when you have like sine and cosine, where they're the derivatives and therefore antiderivatives of each other. That's when you're fairly likely to use one of those as your u. So let u equal 2/3 x. Well, then du is 2/3 dx. Well, I don't have a 2/3 times the dx. So multiply both sides by 3/2, and dx then can be replaced by 3/2 du. And then you need to change your limits of integration. So if x equals pi over 2, then u equals 2/3 times pi over 2. Look, 2/3 times pi over 2. So you get pi over 3. And then if x equals 0, u equals 2/3 times 0. So u equals 0. And we're ready to do our substitution. So it's now from 0 to pi over 3. Cosine, instead of 2x over 3, it's u. And instead of dx, dx is replaced with 3/2 du. That gets us right here. The antiderivative of the cosine of u is the sine of u. So that 3/2 is out in front. The antiderivative is the sine of u. We evaluate it from 0 to pi over 3. So you have the 3/2 in front. need to evaluate the sine of pi over 3 minus the sine of 0. Turns out the sine of pi over 3 is square root of 3 over 2. Sine of 0 is 0. So all you got to do now is multiply 3 halves times square root of 3 over 2 and get your answer. Okay? 103. Everybody done with this one? All right, there's 103. They must be asking us to use even and odd. Yep, evaluate the integral using the properties of even and odd functions as an aid. So on 103, we have the integral from negative pi over 2 to pi over 2 of sine squared of x times cosine of x dx. All right, so that's an even function. That means right off the bat, I can rewrite this as 2 times and then half of it. I mean, you could go from negative pi over 2 to 0, right? But it would be more conventional to go from 0 to pi over 2 of sine squared x, cosine x, dx. Now, we're faced with that. Sine and cosine are derivatives and antiderivatives of each other, with, of course, a negative thrown in. So which one should I choose? Well, choose the one with an exponent on it. Okay? So let u equal the sine of x. Then du will be the derivative of that, dx. So cosine of x, dx. That means that sine squared x is now going to be u, and cosine is going to be du. So it's just going to be the integral of u du. Okay? We still got the 2 out in front, right? Well, what else do we need to do? Well, we need to change our limits of integration. So if x equals pi over 2, u equals the sine of pi over 2. And what's the sine of pi over 2? You can look on the screen. 1. And if x equals 0, then u equals the sine of 0. And what's the sine of 0? 0. So that's the integral we need to evaluate. Right there. Then you do the power rule. Then you do evaluating. Then you do multiplying. And you get 2/3.
Okay, for problems like 103, what is it, once you go to step from u, what if the doing that derivative doesn't work out too well?
Then you need a different u. Because remember, at this point in our mathematical lives, they've made these problems up to make them work. If they don't write that on there, we can't work this problem. Okay? So they've got to give us functions that we're able, because we feel like, we know the power rule and now we know how to use substitution. You kind of start feeling like, yeah, I can integrate anything. No.
What about problems using?
What do you mean?
Is there a situation where we have used rule?
I don't know. Okay. $73. All right. let u equal the quantity that has the exponent on it, so that's x cubed plus 1. You compute du, you get 3x squared dx. The only trouble is, our problem doesn't have 3x squared dx, it has 2x squared dx. Well, what do you multiply a 3 times to turn it into a 2? 2/3. That way you can do that, you get a 2. All right. All right.